13.116 right here involves a spacecraft that's in a circular orbit about the Earth, and we're going to put it in an elliptical transfer orbit to put it out to a larger radius and then go into a circular orbit from there. We're trying to calculate or show that the change in energy of the going from this circular orbit to the outer circular orbit is given by this expression right here. Well, the total energy, of course, is kinetic plus potential, and the delta E would be the final kinetic plus potential minus the initial kinetic plus potential. So delta E would be equal to, well, the initial is the final is 1/2 mv2 squared, which is the velocity for the orbit B, minus gmm over r2, that's the potential, gravitational potential energy, and then you got minus, and you have a 1/2 mv1 squared minus gmm over r1 then for that. Well, when you go ahead and express the V2 circular orbit, it's gm over r2, and circular orbit right here is gm over r1. So what we have is 1/2 gm over r2 minus gmm over r2 minus these terms right here. And you can see there's a gmm over 2 that can factor out everything. And when you do this, you're left with 1 over r1 minus 1 over r2. You'll notice that these terms right here, for instance, 1/2 gm over r2 minus gm is going to leave you with a negative gmm over 2r2. And so there's your negative gmm over r2, 2r2. And this one will do the same thing similarly, but leave you with a positive because it's minus sign out front of a gmm over 2r1. Now, when you simplify this, get a common denominator of r1, r2, you're going to have r2 minus r1 divided by r1, r2. So you'd end up with gmm r2 minus r1 over r1, r2 with the 2 there, and that satisfies what we're trying to find. The next part of the problem is to arrive at the change in energy of the system when you change from circular orbit to the elliptical and then from the elliptical to the circular back over there. Well, that's the delta E that's taking place, and the delta E that's taking place up here is really delta E sub A plus delta E sub B, because once you're in an orbit, energy is being conserved. So the only time you have a change in energy is when you fire rockets here to add some kinetic energy to the system then, and energy is conserved along this path right here, and then you fire rockets again, and then energy is conserved along this path. So what you're going to do is you're going to add the energy into 2 stages, one at A and one at B. Delta E sub A would be a 1/2 m V sub A squared minus 1/2 m V sub A, this is prime squared minus 1/2 m V sub A squared. I didn't put the potential energies here because the potential energy doesn't change at A as you fire the rockets. Only the kinetic energy changes. So the delta E sub A then is given by that expression. You recall that 1 over R1 plus 1 over R2 is equal to 2 gm over R1 squared V sub A prime squared. And then V sub A prime, V sub A unprime squared for a circular orbit is gm over R1. And so when you calculate this or know this, you can plug this in for VA prime. We're going to put in 2 gm over R1 squared, and then all this divided into it. So there's the 2 gm over R1 squared, and then that term right there going into the denominator. And then you got minus 1/2 m VA squared. VA is this right here, gm over R1. Well, this simplifies down to, you see you got a 1/2 gmm in each term, so I'm going to factor that out. And 1/2 gmm leaves you with a 2, and we get a common denominator right here again of this 1 over R1 plus 1 over R2 can be written as R2 plus R1 over R1 R2. So there's the R1, and the R1 R2 is in the denominator, go up here and be in the numerator, and then one of them will cancel out with R1 there. So I'll be left with 2R2 over R1 plus times parentheses R1 plus R2. And then I got a minus 1 over R1 from this term right here. And so when you simplify this, factor out to everything and simplify it down, you'll end up with an expression that looks like this. We can go through, and if you notice the GMM R2 minus R1, there's GMM R2 minus R1 over 2R1 R2, there's 2R1, and I multiply by R2 over R2. And so what we get here then is this term, and then these right here become delta E. And so what I'm left then with is R2 over R1 plus R2 times delta E. And also note then that delta E sub A is delta E minus delta E sub B. So if I want to solve for delta E sub B, I can get delta E and subtract from it R2 over R1 plus R2 times delta E, and I end up with that. And then when you simplify this right here, you end up with delta E sub B equal to R1 over R1 plus R2 times delta E.